Good afternoon and welcome to our webinar on the GCIB, that is the Gas Cluster Ion Beam. Firstly, to introduce ourselves, we are from Ionoptika. My name is Kate McHardy and I'm the Head of Sales at Ionoptika. I'm going to introduce the company briefly and then I'm going to pass over to my colleague, Dr. Bellew, who is our Marketing and Applications Manager. I'm showing you the photo here for two reasons. Firstly, to introduce myself and Alan to you, and secondly, as I think it demonstrates the versatility of the GCIB. This photo was taken last year when Alan and I met with Specs in Germany to discuss the integration of the GCIB 10S in their EnviroESCA system. I'm sure that Alan will refer to this and to the other applications of the GCIB 10S during his discussion later. So, a little bit about Ionoptika. We are a company based in the south of the UK. We are 35 people in total, and we are split between disciplines such as software, research and development, hardware design, test, service, production, and of course, sales and marketing. The company has been going for just over 25 years, and we have a very active research and development department. Proud to say that we do all of our own mechanical and electrical design in-house. We have very strong links with universities across the UK, and we have current collaborations with the universities of Oxford, Cambridge, Manchester and Surrey, to name but a few. We also have customers and collaborators across the world, including the USA, Europe and Asia. As I said, Ionoptika has been in business for just over 25 years, and our first ion beam system was delivered in 1995. That was a floating low-energy ion gun. Over the intervening 25 years, we have developed and delivered a number of other ion beam systems and instruments. The ion beam systems included the first commercial gold cluster source in 2001 and the first commercial C60 source in 2002. Today we're going to talk about the GCIB 10S developed for sputtering. And in recent years we have also developed higher energy versions of the GCIB, a 40 kilovolt system and a 70 kilovolt system optimized for SIMS. And these are used almost exclusively in our J105 TOF SIMS instrument. Now, aside from ion beam systems, we also have two full instruments, a J105 secondary ion mass spectrometer, which has been designed around the use of gas cluster ion beams for SIMS, which makes it exceptionally powerful for use on soft materials such as biological tissue, cells, soft organic materials and polymers. We also have a single ion implantation system called the Q1, which offers deterministic single ion implantation for use in quantum research and manufacturing. We are going to talk exclusively about the GCIB 10S in the webinar today, but we will be having future webinars, including one on the J105 in the coming weeks. So if you are interested, please do sign up to that and speak to UCVAC, our agents, about that. As I mentioned, we are going to be talking about the GCIB 10S today, but I wanted to show you that we have a wide range of ion guns that we can provide. So if the GCIB 10S is not the correct gun for you or your application, or you are interested in what else we can offer, again, please speak to UCVAC, our agents, for more information. So with that, I'm going to hand over to Dr. Bellew, our Marketing and Applications Manager, who is going to give you some further information on the GCIB 10S.
So, good morning, or good afternoon and good evening, depending on where you are. My name is Dr. Bellew. I am as Kate mentioned, Marketing and Applications Manager with Ionoptika, and welcome to today's webinar. I'd like to thank UCVAC for organizing this. I hope it is useful, and obviously we are very keen to work with anybody who has applications, particularly new and interesting applications for the GCIB 10S. So today I'm going to introduce you to the GCIB 10S. I will tell you why you might want to choose a gas cluster ion beam for your next purchase or for your system. I will introduce you to the 10S itself. I will explain how the ion beam operates, as well as some of its key features, and I will go into some of the applications for this gas cluster ion beam. So why might one want to choose a gas cluster beam for their experiments? Essentially, a gas cluster ion beam is a very, very soft means of sputtering material from a surface. And by soft, I mean it introduces very little damage into the sample. These ion beams can be very, very versatile, so they benefit a wide range of applications and different types of samples, because the soft sputtering mechanism provides different benefits depending on whether the material is hard, such as metals and semiconductors, or soft, such as organic tissue or polymers, anything of that sort of nature. So to explain why a GCIB is such a soft sputtering beam, I will use this diagram to help explain. So comparing a monatomic ion beam such as gallium, traveling at high energy, the ion beam penetrates very deeply into a sample, shown here in this illustration as different layers. So each colored layer is standing in for an atomic layer. So a gallium ion beam, for example, but it also applies to something like argon, would penetrate very deep within the sample and actually doesn't produce that many sputtered ions. So it's not a very efficient sputtering beam. It also damages the sample very deep within the surface. So many layers beneath the surface, the bonds have broken. And so if you try to analyze that material, it will be different to the pristine material. As the size of the ion beam is increased, so as we go from gallium to gold to C60, which is obviously a collection of carbon atoms, to something like an argon cluster, the penetration depth reduces and the damage reduces also. The crater size increases, but the actual damage imparted into the sample is reducing in all cases. So an argon cluster beam does not break bonds in the materials that it hits. So that is why it's so useful. So comparing to a monatomic argon beam, if we look at a PET spectrum from an XPS, we look at the C1s peaks, these two peaks here, which are the carbon-oxygen bonds, after sputtering with an argon-1 beam, these peaks have almost disappeared. So those bonds have been broken. Whereas if we compare the pristine sample, which is this black line here, and the argon cluster, sputtering, they're almost identical. So the carbon-oxygen bonds have not been broken. And this is the benefit of argon clusters. The GCIB itself is a very economic upgrade for aging instruments. It can provide a means of extending an instrument's life because it introduces a new means of analysis, whether that be depth profiling, whether that be sample cleaning, etc. So the GCIB 10S itself, so it is a 10 kilovolt argon cluster ion source. We provide a range of presets which allow the user to select the cluster range from all the way from argon 1 to more than argon 3000. In most cases, if the user requests it, we will provide argon 4000 or even argon 5000 as well. Obviously, it provides damage-free etching of organic and inorganic materials. It also is a really valuable means of cleaning a sample. For example, metals, semiconductors, or other hard materials. Two key features of the GCIB 10S are that it provides real-time cluster measurement and adjustment. And I'll go into this in more detail later. We also provide a means of imaging via sample current imaging. And these features are unique to the GCIB 10S. There's also a gate valve for quick and easy servicing so that the chamber is protected. The analysis chamber is not vented to air if the gas cluster ion beam needs to be serviced, or vice versa. If the chamber is being vented, the column in the ion beam can be maintained at high vacuum. So to give you an overview of how the GCIB 10S works, this is a cut through of a typical system. It's a very simple system, really. The clusters are formed in what we call the expansion chamber. High pressure gas passes through a very thin nozzle into a low vacuum region. This results in adiabatic expansion of the gas, which causes it to cool and form small clusters. These clusters can range anywhere from argon 2 to argon 5000 and more. Those clusters are then propelled via jet propulsion into the source region, where they are ionized through electron bombardment, and then accelerated to a maximum energy of 10 kilovolts, though that can be varied. The system is fully ultra-high vacuum compatible. Two very large turbomolecular pumps keep vacuum levels in the column below 5 by 10 to the minus 7 millibar. There's also a gate valve for, as I mentioned, to protect the chamber from vacuum loss. Once the clusters are ionized, a Wien filter allows the user to control the mass of the clusters that reach the target. Cluster size is fully controllable. We provide all of the means so that a user can select the cluster size that they wish. There is no guesswork. We do not provide buttons that the user can just press and hope. So it is fully customizable. And then finally, the electrostatic scan plates allow the user to control the beam on the sample by focusing the beam and directing the beam using the scan plates. So it's a very versatile instrument. Like I said, it's very customizable. And there are various options that can be included on the system, and I'll discuss those at the end. One of the central features of the GCIB 10S that differentiates it from other gas cluster beams is that we allow the user full control of the system. We do provide a range of presets once we ship the system, and they will allow the user to select the cluster size that they wish. And they will usually be tuned for the highest current possible. So, for example, Argon 1000 usually is in excess of 30 nanoamps. However, many variables can affect cluster size. This includes temperature variation, movement in the source region, so the cluster size you think you are getting may not actually be the cluster size you are getting. And we have found that cluster size is a very important parameter for achieving the best results. So knowing exactly what your cluster size is allows you to make adjustments to your experimental parameters to make sure that you're not sputtering too much or too little. So for this reason, all of the parameters on the GCIB 10S are completely adjustable. From the source region, the currents, the acceleration voltages, the grid volts, the repeller volts, every single parameter is available to the user to adjust. And we have a real-time measurement system that allows you to immediate feedback to tell you exactly what the cluster size is. And that actually looks just like this. So here we have a real-time graph of the cluster measurement. Here it's telling us what the cluster size is, what the time of flight is, because this measurement is achieved via a time of flight measurement from the source to the sample. We can tell it what the energy is and what the gas is. Now, this particular screenshot was obtained on another gas cluster ion beam that we provide, which is a high energy water beam. So excuse these numbers, they will not be the same for the gas cluster, the GCIB 10S, but the system, the operating system is exactly the same. So this is a really powerful means of choosing the experimental parameters that you want, that are right for your setup. Some users don't want very much current, so this allows the user to adjust the current levels while still achieving the same cluster size. The other unique feature of the GCIB 10S is that it provides a built-in imaging system. So there is no need to provide external imaging electronics and no need to provide secondary electron detectors. The GCIB 10S imaging system uses sample current as a means of obtaining an image. This allows, on installation, the ion beam to be aligned, focused, and the raster field to be calibrated. This is not the case for other such ion beams. Simply connect the sample current output of your instrument into the electronics of the GCIB 10S and immediately start imaging. It's that simple. This is an example of what the GCIB 10S can see. So this is a screw thread on a sample stage. So the field of view here is approximately 8 millimeters, which is what we specify for a working distance of 40 millimeters. So this allows very convenient setup of the ion beam, particularly when adjusting samples or moving between samples. It allows the user to make sure that they are actually targeting the area that they hope they are, that they think they are. So to go into the applications for the GCIB, they fall under a couple of categories. One is depth profiling. So for XPS particularly, the GCIB 10S is an incredibly powerful tool to obtain very, very high resolution depth profiles, particularly when looking at soft materials, for example, polymers or organic materials. Here we show a multi-layer stack of Ergonox 1010 interspersed with very thin layers of Ergonox 3114. Now the Ergonox 3114 layers are only 10 nanometers thick within a film that is approximately 450 nanometers thickness total. The GCIB 10S is capable of sputtering through this very soft material, this without breaking bonds, and this is evident in the smooth line that we see for the carbon signal. We also see very strong, very clear peaks in the nitrogen signal as the Ergonox 3114 layers appear. So the uniformity of the nitrogen signals is not changed despite etching through more than 400 nanometers of material. So there is no damage being imparted to subsurface layers. So the GCIB 10S is a very powerful tool for depth profiling of this nature. The other main area that the GCIB 10S falls under is sample cleaning. As I mentioned, the damage done to hard materials as well as soft materials is minimal. However, the sputter rate is very different for organic material compared with hard materials. In most cases, it's approximately 10 times faster to sputter soft organic material than it is to sputter hard material. This provides a benefit as it means that hard materials can be cleaned of contamination prior to analysis. So for example, here we show a gold foil that was left unprotected in a drawer for several months. Many layers of contamination built up. 10 minutes of sputtering with the GCIB 10S, and we have removed almost all the adventitious carbon material that had built up on that sample. We also see a 10 times increase in the signals from the gold, which shows that the carbon material was suppressing that gold peak. So it's a very simple but very powerful means of providing the best data possible. Prior to analysis, simply run a quick clean and you can guarantee that your surface is pristine. This can not just be used for XPS, but also for applications such as scanning probe microscopy, so for AFM or for STM, where clean surfaces are vital. The GCIB 10S could be a very, very powerful tool to ensure cleanliness over large areas. So the scan field of the GCIB is, like I said, 8 millimeters. So cleaning an entire sample within a couple of minutes without having to run very intensive heat treatment procedures to ensure cleanliness. Another interesting application that the GCIB 10S falls under and has recently gained prominence is the use of the GCIB to perform high-resolution 3D tomography. So here, researchers combined the GCIB 10S with a high-resolution SEM. To do the work that they needed, they were using techniques such as diamond knife to etch or to remove thin layers of brain tissue. However, this was preventing them from getting very good depth resolution. So they turned to the GCIB. Using the GCIB, they are capable of removing less than 10 nanometers per layer, combined with the very, very high resolution SEM imaging. They recombine this data to get less than 10 nanometers isotropic resolution of brain tissue. This has now been added on to the Zeiss Multisem, which is a 91 parallel beam amazing instrument. And with the GCIB, they can mill large areas of the sample and obtain 91 parallel high-resolution SEM images to do very, very high volume work. And I would highly recommend looking at the paper listed here. It's an amazing set of work, but also is an application that I think is growing. Particularly interest in SEM and TEM integration is something we are seeing a lot of. So to give you an example of what this data looks like when recombined, this movie shows is going through in Z, and the contrast mechanism is through the features of the brain tissue. So we are actually able to see the various features of the brain, such as the blood vessels and the cell walls and all sorts of really interesting regions of the brain. So finally, I'll touch on the options that are available with the GCIB 10S. So as standard, the system comes fitted with an ion source, column, and mass filter. It also comes complete with a pumping kit, as well as a 19-inch rack for the electronics. Sample current imaging is included as standard as well, as is the time of flight measurement system. Also available are pneumatic valves for the gate valve and also the gas in valve. This allows integration into a fully electronically controlled system. If the sample current imaging is not sufficient for your needs, we can also provide a secondary electron imaging system. One of the difficulties around gas cluster ion beams is the predication of large clusters based on different source parameters. And it's actually quite difficult to obtain low clusters. So if low clusters are of interest to you, we can provide a low cluster modification kit. And this allows tuning of the cluster source between argon 1 and argon 1000. For sensitive applications such as SEM and TEM, where vibration is an issue, we can provide a low vibration pumping kit. Where instruments are of non-standard design, we can customize the length of the nose cone such that the working distance is appropriate for your instrument. So we provide a wide range of customization with the GCIB 10S. I hope this webinar has been of use. I'm very interested to hear your questions. and I thank you for your time. I will now pass over to Tao, who will provide hopefully your questions. Thank you very much.